We've seen the general definition of the inverse of a matrix. It's a matrix where when you take it and multiply by the original matrix, you get the identity matrix back. This works for square matrices, and we gave a formula in the case of a 2 by 2 matrix. That formula used the determinant in a very important way. Here we're going to try to give a formula for the inverse of a 3 by 3 matrix, and we're going to do it in such a way that we can easily generalize it to the n by n case. There's a lot more work involved in doing the inverse of an n by n matrix as opposed to a 2 by 2 or even a 3 by 3, but the general principles still apply. So what are we trying to do? We've got A, which in our case is going to be a 3 by 3 matrix, and we're looking for another 3 by 3 matrix, A inverse, such that A times A inverse is equal to the 3 by 3 identity matrix, and A inverse times A is also equal to the 3 by 3 identity matrix. We only have to check one of these two equations, as I mentioned before, and I think in this video we perhaps only check the second one. So what are we going to do? Well, we need to use determinants somehow, and in fact we need to use cofactors as well. So recall that if A is given by these aij's, which means the entry in the ith row and the jth column, then aij, capital A, is minus 1 to the I plus j. That's that checkerboard of pluses and minuses times a determinant. And the determinant that you put here is the determinant of the smaller matrix where you have removed row I and column j. So what we're going to do is we're going to take these cofactors and we're going to assemble them into their own matrix, and then we're going to see what happens when we do that. I've got the matrix aij, little a, and I'm going to form the new matrix of cofactors. So in the 1, 1 position, I'm going to put the cofactor corresponding to the 1, 1 position, and so on. So this is what's called the matrix of cofactors, for the obvious kind of reason that we've taken our original matrix and replaced it with all of the cofactors for the exact same positions. And now I'm going to take its transpose. So what happens when you take the transpose is you swap the rows and the columns. So this first row becomes my first column. The second row becomes my second column. And the third row becomes my third column. This matrix here is called sometimes the adjoint of A, and we use some notation ADJ A. And the adjoint of A is very nearly the inverse. The formula here is that A inverse is equal to 1 over the determinant times the adjoint of A. This is our formula for the inverse of a 3 by 3 matrix. Now, let's write out what happens if we take A times A inverse using this formula and see how all those formulas for the determinant, and in particular all of the instances of the alien cofactor rule, help us to actually show that this is the inverse. We won't go through full details, but we will go through the general idea. Full details can be found in the notes. So we're going to compute and show that A times A inverse using that formula is equal to the 3 by 3 identity matrix. So A is A11, A12, A13. And then our formula for the inverse says we have a 1 over the determinant times the transpose of the matrix of cofactors. So we got cofactors, but we've arranged them in a different way. We have to multiply these together. So what happens when we multiply this top row by the first column? Well, we get A11 times A11, where we have entry and cofactor, plus entry times cofactor, plus entry times cofactor. So in each case, we have an entry of the matrix A times its corresponding cofactor. We've added all those together, and that gives us the determinant. So this 1 over the determinant I will leave out front. And when we multiply this row by this column, we get the determinant. Similarly, if you do the second row and the second column, you'll get another formula for the determinant. So we get another determinant, this time on the diagonal, and the same with the third row times the third column. So all of the diagonal entries are the determinant of A, and that's good because we've divided by the determinant out front. What happens for all the other rows and columns? Well, if we take the first row and say the second column, we get A11 and then the cofactor for A21, A12 and the cofactor for A22, A13 and the cofactor for A23. And if you write that out, what you'll see is that'll be precisely one of the instances of the alien cofactor rule. So we get a 0 for this entry using the alien cofactor rule. And in fact, all the other entries will be 0. So zeros from the alien cofactor rule. And now what we have is 1 over the determinant, and then this matrix which is the 3 by 3 identity matrix once you cancel everything out. Now this uses one side of the alien cofactor rule, and then if you did A inverse times A, you'd use the other. So one of them uses the column version, one of them uses the row version, and in each case we use 3 different formulas for the determinant that go along the diagonal. And this is how you compute the inverse of a 3 by 3 matrix.